Okay, so we are moving to our host, Juan Carlos Santamarta. He's a researcher specialized in water resources, hydrology, geological planning, and sustainability in island environments. He's a professor at the University of La Laguna and also an associate member of the Royal Academy of Engineering of Spain. So, Juan Carlos, hola. We are looking forward to your presentation.
Hello, everyone. Just to say a warm welcome to our speaker, Miss Sileti. She just joined us, and later after my presentation, he is going to present. So, a warm welcome to Miss Sileti from the Pacific Islands. Good morning. Today I will talk about water security in the Canary Islands under climate change. It's fair to say that the islands are very interesting case because they combine tourism pressure, volcanic geology, and climate stress. The Canary Islands are an Atlantic archipelago belonging to the Kingdom of Spain. There are 8 volcanic islands with about 2.2 million residents, and we have every year around 15 million tourists that visit our islands. So for that reason, tourism is a key part of the economy. So water availability is closely linked to economy stability. Our main economic sector, as I said in the last slide, are tourism, agriculture, and service. Tourism requires water for hotels, pools, and landscaping, and our agriculture also depends on irrigation, especially crops like bananas, as our speaker Benoit says in Martinica. And the urban growth adds additional pressure on the system. The islands have volcanic geology, as I mentioned, steppe terrains, and strong climate gradients over very short distance. Because of these factors, water management is more complex than in a continental region. For that reason, we are here now sharing this experience. If we're talking about the volcanic aquifer, you can see these two pictures. On the left, you can see our aquifer scheme. It's a basic model, but it's very useful. This came from Hawaii Islands. We can use it in some of our islands. So on the left part, you see our aquifer is overrised. For that reason, we can extract the water with horizontal galleries. And in the second picture, you can see our main waterworks for extract groundwater. It's mainly water galleries, as I mentioned, deep wells, inclined shafts, and springs, of course. All that groundwater is stored in our volcanic aquifers, and these aquifers behave differently from continental aquifers because water moves through fractures and volcanic layers. So historically, the islands developed water galleries and wells, as I mentioned, and these horizontal tunnels captured groundwater inside the mountains and were essential for agriculture. Just only in Tenerife Islands, we have more than 1,500 water galleries. Today, the islands use several water sources: groundwater, desalinated seawater, reclaimed wastewater, and small surface reservoirs, mainly in Gran Canaria and in La Gomera. More than 100 water reservoirs we have. This diversification helps adapt to water scarcity, but increase energy demand. This is a picture of our annual precipitation. This graphic displays the mean annual precipitation across the Canary Island. The archipelago averages between 150 to 300 millimeters per year at lower elevation through highlands areas on the Western Islands can receive up to 700 to 900 millimeters. This places the Canaries among the driest island archipelagos in the Atlantic Macaronesia region, of course. For comparison, the Azores, located farther north in the Atlantic, receives around 800 to 1,000 millimeters annually, making them roughly 3 to 4 times wetter than the Canaries. Other example is Madeira, is situated just 400 kilometers to the north and can receive up to 2,800 millimeters in its mountainous interior. Through coastal areas are considerably drier. Or the last example, Cape Verde, our neighbor to the south, is even drier than the Canaries, receiving under 250 millimeters per year in most areas. So in the case of the Canary Islands, we can say that we have three main groups: the Western Islands, La Palma, La Gomera, El Hierro, Central Islands, and Eastern Islands. Of course, the water sources vary by islands. Western Islands rely more on groundwater. In the case of the El Hierro, is half of the water came by desalination plants, while Eastern Islands depend heavily on desalination because rainfall is lower. If we're talking about the water supply sources by islands, this table shows the water supply mix for each island. The key takeaway is that Eastern islands like Lanzarote and Fuerteventura depend almost entirely on desalination, while Western islands like La Palma and El Hierro still rely mainly on groundwater. Gran Canaria and Tenerife use a blend of all sources. This island by island diversity demands tailored management strategies rather than a one-size-fits-all approach. So the water used by sector, water demand is divided between agriculture, urban supply, and tourism activities. In some islands, agriculture still dominates, as you can see there. Tenerife is quite half of the water goes to the agriculture. The stream case in La Palma is close to 90% of the water demand is by the agriculture, or El Hierro y La Gomera is more than 50% of the water resources goes to the agriculture. But tourism and urban demand have increased strongly. Is the case of Gran Canaria, even Tenerife, Fuerteventura, and Lanzarote. We have to talk about the climate change, of course. Climate change is hitting the Canaries on four fronts simultaneously, because we have less groundwater research, more frequent droughts, saltwater intrusion into coastal aquifers, and higher evapotranspiration from rising temperatures. These pressures compound each other, creating a vicious cycle of declining water availability at the time when demand keeps growing. Yeah, it's quite the same than the other cases. The structural challenges are clear: rising demand, heavy dependence on energy-intensive desalination, high energy costs in a region still relying on imported fossil fuels, and fragmenting water system with no interconnection between islands. Each island operates an isolated water system, which limits flexibility and resilience. So the current challenges, I think that we have four urgent issues right now. Aquifers being pumped faster than they recharge, with saltwater already contaminating coastal wells. Another thing is the pipe networks losing up to 50%. It's the same like the case that Benoit said. Um, so tourists consuming 2 to 3 times more water than residents. That is an important data. And governance splits across dozens of entities with no effective archipelago-wide coordination. So for the water matters, we have several authorities: Water Council in each island, Canary government, and many others, councils. Water governance is uniquely complex. Each island has its own authority, public and private operators, because much of the quantity of water it's on private hands. That is interesting fact. But public and private operators coexist, and centuries-old water rights systems still shape who owns and distributes the resource. This model work is historically, but now prevents the integrated, efficient management that archipelago urgently needs. So talking about the future challenges, looking ahead, four risks stand out. Serving energy costs for water production as desalination becomes central, of course. That climate uncertainty that complicates long-term planning, that is important too, and intensifying competition for water between tourism, agriculture, and urban supply. And finally, the aging infrastructure nearing the end of its useful life across most islands. In our case, in the case of Tenerife Islands, we have channels with more than 100 years old. That implies a lot of water leakage. So just for safe, some numbers connected to climate change. The temperatures, we have evaluated that the temperatures is rising from 2 to 4 degrees Celsius, precipitation dropping 10 to 30%, and drought risk rate high. Together, they mean less water coming in, more water lost to evaporation, and greater demand for irrigation and cooling. So talking about tools we have developed in the university, coordinated by Noelia and me, for instance, is this climate projection in the Canary Islands that we want to transfer to other islands, archipelagos. This map comes from SICMA Canarias platform. You can download with this code, and it's developed specifically for the Canary Islands under the EU Horizon 2020 Arsinoe project by Climate Research Foundation, Meteogrid, and us, University of La Laguna. This platform provides projection and extraordinary 100 by 100 meter spatial resolution, making the most precise tool for its kind for the islands in Europe. And the greatest challenge was capturing the extreme microclimate diversity of the archipelago, as I told before, where you can move from arid coastal desert to humid cloud forest within a few kilometers on the same islands. What are the variables evaluate? Pues, the variables include maximum temperature, minimum temperature, mean temperature, precipitation, potential and actual evapotranspiration, water balance, the SPEI drought index, aridity index, and heat waves. The projections are generated from 10 climate models under 4 emission scenarios, production 40 different projections for 3 time horizons from 2021 to 2050, from 2041 to 2070, and the last one is to 2071 to 2100. So this means that the platform provides climate intelligence all the way to the end of the century, which is essential for long-term water planning and infrastructure investment decision. Yeah, I think we think, Noelia and me, that this will be an important tool for all the archipelago systems in the future. So just some key points about SICMA Canarias. First, the platform is the very high resolution, as I mentioned. The platform is designed for volcanic island, not a homogeneous continental territory. It goes beyond temperature and precipitation, as I mentioned, many variables that you can use for your water planning in your island. Integrates all last scenarios and with a long-term perspective. And one thing that is interesting, that is the platform is open access. That is important. All the citizens can use it, can download all the data, and we think that this is very interesting. So anyone from the policymakers to farmers can consult projection for their specific location. I think that could be very interesting for that. Just one example to use this platform in La Palma Islands, for instance, the slide illustrates a critical point. For instance, climate and water variables must be analyzed together, not in isolation. For instance, La Palma, this is a perfect example. If we look at precipitation projections alone, the model actually suggests a slight increase in rainfall. That is, I think, very, very, very singular, right? Because you could think that in the future the rainfall is decreasing, but in this case, it's increased. So at first glance, that sounds like good news. However, when we factor in rising temperature, the pictures change dramatically. Higher temperatures drive greater evapotranspiration, meaning more water is lost from soils and vegetation back into the atmosphere. The net result is a negative water balance and less natural water resource availability, despite receiving more rain. This is why tools like SICMA Canarias are so valuable. They allow us to cross-reference multiple variables simultaneously and avoid dangerously misleading conclusion based on a single parameter. So this is a good example. Another thing, a special thing that I want to share with you is our Sea of Clouds. I think that Martinica has something similar, and probably in other islands like us, for instance, Madeira and other archipelagos has this kind of Sea of Clouds. Um, and I think this slide addresses a fascinating and alarming phenomenon, the descent of the Sea of Clues in Tenerife. The Sea of Clues, formed by trade winds hitting the island's topography, is fundamental for maintaining humidity in the unique Canarian forest, the Laurel forest, or we say Laurisilva or Monteverde. These are a singular ecosystem of extraordinary biodiversity. The problem is this. As sea close descends, the vegetation belt it sustains will be forced to shift lower to lower elevations. But this is simply not possible because those lower areas are already occupied by cities, roads, and infrastructure. Initially, we assumed that rising temperatures will push the sea of clouds upward, since warmer air should leave the cloud layer. However, what actually controls the cloud position is the thermal inversion layer created by the trade winds. As temperatures rise, this inversion layer strengthens and pushes downward, acting as a barrier that forces the sea of clouds to descend rather than ascend. The clouds move down and the vegetation must follow, but it has nowhere to go. This is one of the most counterintuitive and devastating effects of climate change in the Canary Islands. For that reason, I want to share with you. And the last tool, sorry, the last tool that we have developed is another advancement that we have developed in our university, coordinated by Noelia and me. Is in 2 weeks we will be officially launched the cascading-failure platform. And this tool, aims to identify the critical nodes linked to water infrastructure across the islands and to model how natural hazards such as landslides, forest fires, earthquakes, and volcanic eruption can affect those nodes and trigger chain reactions throughout the system. All of this is framed within a climate change context, which the platform also incorporates. The idea is simple but powerful. If a wildfire destroys a key water gallery, what happened downstream? Which communities lose supply? Which agriculture areas are cut off? By mapping these dependencies and cascade failures, we can prioritize investment, design redundancy into the system, and prepare emergency response plans before disaster strikes rather than after. So this could be a very good tool for our archipelagos too. That is very interesting. So to finalize our future challenge and solution, I think that we have 6 concrete actions. Close the water cycle with wastewater reuse, power desalination with renewable energies, modernize leaking networks, recharge overexploited aquifers, and unify governance across islands and change the water culture among residents and tourists alike. These are not aspirations, but necessities if the archipelago is to remain habitable. So to conclude, I think some sentence, water security in the Canary Islands depends on 4 fundamental pillars. Diversify water sources so we are not dependent on any single supply. Energy water integration to make desalination sustainable. Adaptive governance that can respond to changing conditions and climate resilience planning that prepare us for an increasingly arid future. The Canary Islands can be a global model. We thought that for how islands territories addresses water security under climate change, but only if we act now with determination and coordination. So that's all for my side. You can reach me at the University of La Laguna for further collaboration on water research in island territories. Thank you very much.
Thank you, Juan Carlos. And thank you very much for presenting SICMA Canarias and our cascading failure platform. I think they are two very powerful tools we have developed from the University of La Laguna and that really help about climate projections and adaptation to the climate change. So thank you for showing to our audience these tools.